Hi everyone, my name is Mukarram Zubair, and here I'm going to present you regarding the recent progress and the future recommendations for one of the emerging adsorbents, biochar layer double hydroxide composites for the removal of different type of pollutants from water. The outline of presentation includes the background in which I will give you some overview about the layer double hydroxides and the biochar for wastewater treatment. Uh, then I will discuss with you about the biochar, LDH composite, the physical and chemical properties, what are the factors affecting the properties of biochar LDH composites, application of biochar LDH composites for the removal of different type of pollutants, and what are the mechanism, purification mechanism, interaction mechanism with these pollutants. So how, based on what mechanism they are removing these pollutants. Uh, Reusability performance, which is one of the important factor of different type of adsorbents. And finally, I will show you some future recommendations. There are a lot of work, research gap has to be done in order to exploit the complete utilization of biochar. So layer double hydroxide, basically, they are layered structure of mixed metal ions. If you can see the structure here, the mixed metal ions, divalent or trivalent metal ions are surrounded by hydroxyl groups. And these have a layered structure. And between these layers, you can see it here, between these layers, it contains anions and water molecules. So the anions could be carbonates, nitrates, chloride, depending on what type of precursor salts you are using. So they showed highly promising characteristics for the removal of different type of pollutants because they have excellent anion exchange capacity. And because the versatile composition, you can prepare different type of layer double hydroxides with different like magnesium iron, magnesium aluminum, cobalt iron, cobalt aluminum. So they have a versatile range of composition. Even the toxicity of these materials is comparatively low compared to the other type of materials. The removal performance is comparatively very fast. You can see it here from the literature. I can show you from 20 to 120 minutes, it can remove the pollutant from the water phase. The efficiency is comparatively higher compared to the other type of materials, and even the reusability performance of these materials is very good. So they showed highly promising characteristics for the in water purification technologies, but there are certain limitations which not allow them to be commercialized because they have lower stability. They cannot be worked at lower pH range. If suppose the wastewater is highly acidic in nature, so there is a possibility of these materials to dissociate. So this can produce the secondary pollution. Similarly, because these particles are in nano size, so there's a possibility of agglomeration. So and also the cost of that material is comparatively high compared to the commercially used materials like activated carbon or other type of materials. Biochar, as you know all about, it is the product obtained from pyrolyzing of different biomasses. So it showed promising characteristics for different applications, environmental application. It is used for soil conditioner and also for water purification and carbon capture technologies. Because these biochar, it is abundantly available, low cost, and when you pyrolyze the biomass, the structure of the biochar is highly porous in nature, and it contains a lot of functional groups, and the surface area is also good. And the stability, if you can see the stability here, because it is purely carbon, so the stability of that material is comparatively good in wide pH ranges. But still, for water purification technologies, the performance of biochar for the removal of pollutants is not that good. The removal performance is not that good, and even the removal rate is very slow. So it takes about 12 hours to 24 hours to remove the pollutant from the water phase. And the reusability performance, if you think about, the reusability is very low. So this limits the use of biochar for water purification technologies. So if you support the biochar with layer double hydroxide, a new material which is called biochar LDH components, uh, resulted with improved surface characteristics, functionalities, and surface area, and also the morphology. So you will have a more sustainable and eco-friendly material, and the removal performance of that material for different type of pollutants is comparatively good compared to the LDH alone. And also you can say for the biochar. I will show you in later slides that how the removal performance comparatively better with the pure biochar and the pure LDH alone. So these are the this is the graph which shows you the recent investigations have been done on biochar LDH composites, especially for water purification. So the first article was published in 2019, and from last 5 years, a lot of work has been done, is going on to exploit the use of biochar for water purification. Generally, if you see the pie chart here, uh, around 30, most of the work has been done for the removal of anions. Anions mostly focus on phosphates. So the biochar and LDH components showed high affinity towards the phosphates, and also it has been utilized for the removal of heavy metals like lead, cadmium, chromium, and some pharmaceutical pollutants, antibiotics. Most of the and it showed highly promising high removal performance for the antibiotics and dyes as well. Now, physical and chemical properties of these biochar LDH components, because these are the important properties which can lead to better removal performance, better stability of the composite. So these can be controlled by considering four major factors. The first one is the synthesis route. What synthesis route you are going to adopt? So in previous studies, generally three synthesis methods have been used: hydrothermal technique, co-precipitation technique, and co-pyrolysis technique. In hydrothermal technique, if you can see it here, it requires the biochar mixed with the metal oxide, metal salts, to LDH metal salts. Then it put into the hydrothermal reactor and heated for about 110 to 160 degree. And it resulted in a biochar composite with good dispersion of heavy metal layered nanoflakes on the surface of the biochar. The crystallinity is also very good, and the surface area is comparatively good. In co-precipitation method, generally the biochar mixed with the metal LDH precursor salts, and the solution, the pH of the solution is then increased to about 10. So when the pH is increased, the metal ion starts to precipitate on the surface of the biochar. So it leads to more uniform distribution of the LDH flakes on the biochar, leading to better surface characteristics, crystallinity, high surface area. And this method, co-precipitation method, the main advantage is that it can be scaled up to produce large amount of biochar. Recently, this process has been investigated by different type of authors to produce biochar LDH composite. That includes first, the biomass is co-precipitated. The LDH is co-precipitated on the surface of the biomass. Then it is again calcined. You can see it here in the third picture. After co-precipitation, it is now calcined to about 300 to 700 degree to produce biochar LDH composites. So in this method, you will obtain calcined LDH biochar composites. So what I mean from calcined, because when you heat, when you pyrolyze up to 300 to 700 degree, the structure of the metal ions, the crystallinity of the LDH breaks. So you will have layered more oxygen growth on the surface. So and this method can also be scaled up to produce large amount of biochar. Second parameter, which is most important, is the mole ratio of LDH. So Lee et al. Investigated, prepared different biochars or different mole ratio. You can see it here. He prepared 2:1, 3:1, 4:1, and 5:1 magnesium aluminum with LDH biochar. And what he found, and that increasing the ratio increased the interlayer spacing, because these are the flakes, and between them there's a anions. You can see it here. And 2:1, the orientation of the anions is perpendicular. When it increased to 3:1, it now changes to parallel in nature. So the orientation is changing, which reduces the interlayer spacing, and it also reduces the charge density. You can see it here. When the LDH is formed from 2:1 to 5:1, the charge density reduces from 4.11 to 2.18. So this significantly affected the surface characteristics like surface area, pore volume, and pore diameter of the final biochar LDH composite. So he also found it, you can see it here in the second graph, that 2:1 showed higher removal performance for the better removal performance for phosphate compared to the 5:1. So the author stated that attributed the reason because of the interlayer spacing, because the 2:1 has higher interlayer spacing compared to the 5:1, so which this leads to trapping of the phosphate more compared. Similar behavior was also reported by other authors like Meli et al. And also Peng et al. The third factor, which is very important, is the LDH biochar mass ratio, that how the percentage of LDH is incorporating onto the biochar surface. So Chen et al. He produced biochar of different mass ratios on the surface, LDH on the of different composition on the surface of biochar, and he found it very interesting behavior, that increasing the concentration of the LDH on the surface of the biochar from 10.7 to about 21.8, the removal performance of the composite for the for methyl orange and chromium starts to decrease. So the reason behind this is the surface area. You can see it here, 13.8, the surface area of the 13.8 LDH biochar composite around 1273. With increasing the concentration, the surface area starts to decrease. So this is due to the blocking. When you increase the concentration of LDH on the surface of biochar, this may possibly the blocks the pores which are present on the surface of the biochar. This may block the pores of the surface, block the pores of the biochar, which leads to the decrease in textural properties like surface area, pore volume, pore diameter. In another study, Wang et al., what he found, that by increasing, he prepared magnesium aluminum LDH biochar of different composition, 25% and 40%. And what he found, by increasing the concentration to 40%, the removal of phosphate is comparatively higher compared to the 25%. So the author attributes this reason that by increasing the concentration of LDH on the surface of biochar, the functionalities also increases. So this promotes the removal. This facilitates the removal of phosphate. So different behavior. So in order to design the biochar LDH component, you have to consider that or what composition you have to coat on the surface of biochar. The feedstock, the fourth factor, which is very important, is the feedstock, that what type of feedstock you are using, and the what type of LDH precursor salts you are using for preparation of biochar LDH components. Generally, the feedstock is available is agriculture waste, sludge waste, animal waste. And in most of the studies for the production of LDH biochar composites, agriculture waste have been utilized. This is due to the reason that they are abundantly available, and the structure of the biochar obtained from agriculture waste is more porous compared to the sludge waste and animal waste. So that's why for the removal of pollutant, they need more porous structure. So that's why most of the studies focus on the agriculture waste. Similarly, LDH precursor salts, different type of salts have been utilized to produce LDH on the biochar, such as magnesium aluminum, magnesium iron, nickel iron, copper aluminum, copper iron. So these directly, because these LDH precursor salt had different type of charge density, different hydrophilicity. So these type of adsorbents, these type of LDH precursor directly affect the structure, functionalities, and stability, and macro and micro porosity of the final product. So which directly affect the removal performance of different pollutants. Now, if you come to the removal performance of these composites, LDH biochar and their mechanism, for the removal of phosphate, they showed highly promising uptake. You can see it here in the first graph. The LDH biochar composite showed high removal performance, up to 150 milligram per gram compared to the LDH alone and also the biochar. So by combining biochar with LDH, the removal performance significantly increased. This is due to different behavior because of the synergistic effect, because of the increase in surface area functionality, which leads to the better removal performance. Even you can see it here, these LDH biochar composites showed better removal performance at different pH ranges. So this is quite attractive for treating industrial waste as well, because the pH of the wastewater is around 7 to 8, so it can be easily used for the treatment of industrial effluent. Plus, in second graph, you can see Zhang et al. He found that within 30 minutes, 95% of the phosphate has been removed by LDH biochar composites. The third graph, you can see it here, the presence of coexisting ions. Because in real wastewater, it consists of a lot of coexisting ions. The LDH biochar, you can see it, the first one. This is without the coexisting ion. The removal performance is around 94.2. But with the presence of other coexisting ions like chloride, nitrate, bromide, sulfate, carbonate, and mixed ions, the removal performance not significantly affected. So this shows very promising results, and it indicates that it can be easily used as a commercial adsorbent for removal of phosphate from real wastewater. For the removal mechanism for the phosphate, you can see it here. Different mechanisms have been proposed that how the phosphate is removing using LDH biochar composite. Because the phosphate generally in from 2 to 7, the phosphates are available in anionic form. So what happened from 2 to 7, the surface structure, the surface charge of the LDH biochar composite is positive. So what happened? The negative ions are attracted by electrostatic attraction. And plus, these LDH composites contain oxygen group, so they form complexes with phosphate, monodentate complex and bidentate complexes with the magnesium oxygen in this. And the presence of functional groups on the surface of biochar also form complexes with phosphate anion. So the combined effect, the multi-mechanism leads to better removal performance of the phosphate from the water phase. Similarly, for the removal of heavy metals, because of highly porous structure of the composite and the availability of functional groups, leads to better removal of heavy metals from biochar. You can see it here in the diagram. The divalent, the copper and magnesium divalent are removed by LDH biochar by three major mechanisms that include surface complexion. The heavy metals like copper and lead, they've interacted with oxygen functionalities of the LDH and form surface complexes. The second mechanism that includes precipitation. So because these LDH contain OH groups and carbonates or nitrate groups between the interlayers, so what happened? This lead or copper, they form precipitates like lead carbonate or lead hydroxide uh, and trapped into the surface of the LDH biochar. Plus, the other mechanism may involve physical adsorption or precipitation with the surface of biochar itself. So, due to the presence of different mechanisms, the synergistic effect of biochar and LDH in the composite leads to better removal performance of different heavy metals. For chromium heavy metal, for chromium 6, generally the chromium is present in the form of anionic form. So what happened? Most of the studies have reported that the chromium 6 is reduced to chromium 3, and this chromium 3 is then replaced with aluminum, which is present on the surface of biochar. So, and most of the chromium, anionic chromium is attracted by electrostatic attraction and forming hydrogen bonding. So based on this mechanism, the removal is comparatively higher. You can see it here, the maximum adsorption capacity of LDH biochar composite is around 680 plus 74 and 330 for different heavy metals, which is comparatively better compared to the other type of adsorbents. Similarly, they showed also very high removal performance, also reusability performance for different type of pharmaceutical emerging pollutants. And you can see it here in the second line for different type of pollutants: tetraxylene, difluonic sodium, carbon tetrachloride, sulfur methazole. These are the antibiotics which are used for different applications. So they showed highly the LDH biochar composite showed high removal performance, around greater than 2000 milligram per gram from the water. Even for the dyes like crystal violet, methylene blue, methyl orange, the removal capacity is greater than 300 milligram per gram. If you look onto the removal mechanism for organic pollutants like pharmaceuticals and the dyes molecules for the pharmaceutical, normally these organic pollutants contain benzene ring. So what happened? They form the pi-pi interaction. They are removed. They interacted with the surface of the biochar LDH using pi-pi interaction. Plus, the LDH contain hydrogen bonds, oxygen, so they form hydrogen bonding. And even in one of the mechanisms proposed by Z et al, X10 et al, that the tetrasilene chloride, you can see it here, the OH groups and carbonate groups present within the layers, they are now exchanged with tetrasilene pollutants. So the tetrasilene is coming inside, and OH groups and carbonate groups are coming outside. So this is anion exchange mechanism. The presence of OH groups can form hydrogen bonds, and plus this is called pi-pi interaction. Similarly, for the dyes, this is for the crystal violet dye removal performance. So it electrostatic interaction, pi-pi interaction, and hydrogen bonding, and also the pore filling failure, because this is highly porous in nature. So these dyes molecules are small, and so they trap into the pores via intraparticle diffusion mechanism. So there are different mechanisms involved for the removal, which leads to better removal performance. Now, reusability performance is one of the important factors to assess to determine the economic feasibility of the material. If the reusability is high, the process cost will definitely be low. So if you can see it here from different studies, the lanthanum ferrite biochar composite showed very high removal performance of phosphate and up to 5 regeneration cycles. The removal performance is almost same, up to 100%. So which is comparatively attractive and promising. Similarly, for lead ion, using magnetic biochar composite, the removal, you can see it here, the removal performance, the adsorption capacity reduced to about 10% up to 5 regeneration cycles. Similarly, here you can see it here, Mali et al. Also reported he removed methylene blue using methanol and sodium chloride, and he found the removal is decreased from around, you can see it here, from 65 to around 50%, which is also quite good. So different regeneration reagents have been used, like sodium hydroxide, methanol, ethanol, acetic acid, or sodium chloride to regenerate these LDH. The high removal, most of the studies, most of the authors reported the high regeneration performance of the LDH biochar composite is due to the structure stability, because the structure normally the low reusability performance is due to structure destability, because during regeneration what happens, you are treating with different chemicals, so the structure breaks. So the structure stability gives you the high removal performance. So some future recommendations, still a lot of work has to be done in order to exploit the complete utilization of biochar. So number one is toxicity analysis. Still, there is no work has been done regarding the toxicity analysis, because the biochar is now coated with LDH, with different metal ions. So there is a possibility that they may leach into the water. So it can produce secondary pollution. So there's a still gap needed. Still investigations need to be required to check the toxic leaching of the LDH biochar composite during the removal performance. The real wastewater treatment, generally the investigations have been done to treat synthetic water or laboratory based. So real wastewater treatment is still, because these real wastewater contain different anions, cations, and different coexisting ions. So the removal performance of the LDH biochar composite should be investigated in real wastewater. Microwave and ball mill. As I told you, based on the previous studies, 3 routes have been investigated: hydrothermal, co-precipitation, and also the co-pyrolysis. So still there's a research gap that other techniques like microwave or ball mill, which is chemical free techniques, should also be utilized for the production of these LDH biochar composites. and should be compared the properties, the removal performance with other previously investigated techniques. Other biochar feedstocks, as I told you, that most of the studies have been focused on agriculture waste. So there is still demand that other type of feedstocks, like from industrial waste, or you can say animal waste or other type of waste, should also be utilized to produce LDH biochar composites. LDH precursors as well. Most of the studies have been done to, they have used magnesium aluminum or magnesium iron and coated on the surface of the biochar. But there are other type of LDH precursor salts, like you can prepare copper iron, cobalt iron, cobalt aluminum. So there's a wide variety of LDH precursor salts. You can make a lot of combinations. So still, there's a lot of work has to be done to completely exploit the removal performance. So the other toxic pollutants should also be explored. The removal performance like phenols, polyaromatics, nuclear pollutants should also be considered to remove these pollutants by using LDH biochar composites. Plus, recently the biochar LDH composites have been utilized as an adsorbent for the removal of pollutant. But there is still research gap to use the same material for desalination technology and as well as for photocatalysis. So these are certain future recommendations which I have proposed, which can be done. So thanks for listening. If you have any question, I'm ready. I'm glad to answer.
Thank you very much, Mukarram. Nice presentation. Thank you. So for the audience, if you have any questions, please just unmute yourself and ask directly or write them in the chat if you want to ask. So you already got your first question. How LDH get bound on biochar?
How LDH get bound on the surface on the biochar?
Yes.
Generally, it is co-precipitated, so it forms the linkage. It traps. It is coated within the biochar surface. So this is because you are heating at high temperature up to 100 degree for about long time, and also the core precipitation. So it is chemically interacted with the biochar surface.
Next question is how do different regeneration agents affect the removal efficiency?
Yeah, these things you can, based on the previous study, you can study that what type of pollutant you have removed. Generally, if you are removing the pollutant at lower pH, acidic pH range, so this pollutant should be removed, dissolved from the LDH surface at alkaline pH. So this is the phenomena. Then this is the mechanism we normally follow. That alkaline pH, definitely it is adsorbed via electrostatic attraction. So at an alkaline pH, it may dissolve easily. So different studies have used different type of regeneration agent, like if they are using, they have used hydrochloric acid, they have used acetic acid, they have used sodium hydroxide, methanol, and ethanol. So based on the previous study, what type of pollutant you're removing, you can decide which regeneration agent you can use.
So you got a couple of other questions. So first one was about the economics of LDH biochar composites. How
regarding the cost?
Yeah, so how close are these for commercial products, and how do they compare to existing removal methods?
Yeah, these things should be considered because still there is a research gap, big research gap should be filled. So nobody has done the life cycle assessment, the cost analysis should be done on these type of LDH biochar composites in order to attract the industries to work on it. So still there is no more work should be done. Up to date, there is no study available because I was working on this review article regarding LDH biochar composites. So I have found no article that who have evaluated the cost analysis or LCA, life cycle assessment of this type of composites.
So, so how much does LDH cost? How much does LDH cost per I don't know in what kind of
Yeah. In a recent study, we calculated the cost because one of the reviewer, he asked about the cost of the LDH. So in recent study, we because we produce in very lab scale, very small amount. So the cost is comparatively high around compared to the activated carbon, the commercial activated carbon which is used for the treatment of pollutant. But the reusability performance of the LDH, because it's used for different cycles, 5 cycles, 10 cycles, so the running cost, including the running cost, the production cost, is comparatively $2 per gram.
Okay. And a lot of questions going around the same topic. So how close do you think are these for commercial to become commercially available? How much research gap is still to bridge?
Yeah, still more because I told in my presentation that most of the work has been done on laboratory based. So there's still more demand and more work needed to be work on real wastewater. Maybe nobody has done work on the column study. They have used the batch studies. So the batch column study, the batch study. So there's a need to do the column studies in order to get better understanding. In one or two studies, I have found that they have done the column studies and they found quite promising results. So, but still, for different type of pollutants, especially the phosphate, because so it has to be done on commercial level. We have to design a column and treat some real wastewater, industrial wastewater or sewage wastewater for the removal of this phosphate or different type of pollutants. And even the main advantage of this LDH biochar composite is that, but after removing the phosphate, the LDH is now exhausted with phosphate. So what happened? It can directly use as a fertilizer, because biochar itself is used as a soil conditioner, and it contains the phosphate as well. So it is now for phosphate rich biochar. So it can be directly used as a fertilizer. So there will be no waste. So it can be used directly to improve the product of the product, the quality of the product for the soil.
So I think we used answer two more questions. So first one, what's about the physical integrity of the particles? So are they physically stable enough to be reused after the application? I think that's what the question is about.
Yeah, Judge, because we did a lot of experiments. The integrity regarding this integrity, what the morphology he is asking, I didn't get the question exactly.
I think it's about the physical retrieval of the adsorbent from the water after adsorption. So do you get them out in the same shape as the biochar particles?
Yeah. So after removal, normally if the biochar, because there are certain type of biochar, LDH compounds, some biochar are magnetic in nature. So you can remove by using the simple magnetic, by using magnetic field. So we did but after adsorption, there are a lot of studies. They did some different characterization techniques. They did some characterization of the composite surface morphology, XRD, crystallinity, and they found it good that after adsorption, the structure of the composite retained same before adsorption. So this is quite promising results, that the structure does not affected due to the removal.
And so the last question now, can coconut shell activated carbon be used instead of biochar? So do you have to use biochar, or can you do activated carbon composites same way?
But yeah, you can use activated carbon composite. But again, the problem is that when you produce activated carbon, the production cost significantly increased. For activation, you need the high energy, maybe some, if you are doing physical activation, you have to do it high energy. But if you are doing, suppose if you are doing chemical activation, you have to use chemicals. So biochar, if you are using biochar with LDH, the cost comparatively lower compared to the activated carbon LDH.
Okay, thank you very much, Mukarram. I think we have to go on to the second presentation. thanks for a really nice presentation, and I'm sure you will be open for any questions if someone has her email.
Okay, thank you so much.